Hello everyone, and thank you for being here. And I'm Luca Corbucci. I'm a PhD student in computer science at the University of Pisa. And in my free time, I also have a podcast. This one, it's in Italian, so maybe it's not useful for everyone here, but it may be a starting point to learn Italian. During my PhD, I'm working mostly on responsible AI, and especially on the privacy-preserving machine learning, model fairness, and sometimes also on explainability. And what I've seen talking with people is that most of the people knows about problems like the unfairness of the models. So it's like a model that is unfair towards a certain group. Most of the people know about the problem of the explainability of the model, because we know that we are using models that are not always explainable, so we don't know what exactly they do. But it's not common that people knows about the privacy risk that may arise when you when we train a machine learning model. So today I would like to try to explain why should we care about privacy when we train machine learning models, and what could be the problems that may arise when we train models. I want to start with a brief introduction about some attacks that we can do against neural networks. There are several possible attacks that can we do. I think that maybe some of you this morning there was a workshop about this topic, so many of you may already know something. I want to introduce just maybe the simplest attack that is called membership inference attack. This is, and I will introduce it in the simplest ways possible, because there are even stronger attack with respect to the one that I will describe, but I think that this is a simple introduction that can give an idea of how this attack works. Basically, when we train a model, we have our dataset. We train a model that is able to predict, in this case, the color of the cat. And an external attacker wants to know if a certain image was used or not during the training of the model. So, in the simplest attack that we can think, that is this called membership inference, as I said, and it was presented in a paper a few years ago. Basically, the idea is that we query the model multiple times with different images. And what happens is that intuitively, the model will answer with different confidence vector. So it will give us a prediction, but it will also give us the probability of the different outputs. And what happens is that usually what happens is that if the model already saw the image during the training, the model will be more confident toward a certain class. Instead, if the model didn't see the image during the training, the model will be less confident. So we will maybe in the end we will predict the correct class, but at the same time the other probability will be higher. And so basically this model will be less confident than the second one, and this is the intuition behind this attack. So what happens is that we train a second model that mimic the behavior of the first one, and then we use some images that are in our training dataset of the model that mimic the first one, to find a threshold between the confidence of the model with the images that are present in the training dataset and the confidence of the images that are not in the training dataset. And based on this threshold, we are able to say this image is probably in the training dataset, this image is not in the training dataset. This is, as I said, just a simple attack. There are other ways to attack models, and there are also stronger membership inference attack that were developed in a few years ago. There is another thing that I think it's important to mention, that is that machine learning models are really good in memorizing some sensitive information about the training dataset. There is an interesting paper about the unintended memorization of these models, of the sensitive information. And there is this paper that describes how they were able to attack a few years ago now GPT-2, that is now an old model, but in that case they were able to extract some sensitive data contained in the dataset. So this is just a funny cartoon about what could happen. So this is a real problem. I hope I convinced you. Luckily, there are many defenses against these problems. Some of them are more formal, some of them are less formal. The golden standard now, and my favorite one, is the use of differential privacy. That, as I said, it's the golden standard. There are people that are complaining about it. I honestly like it, and I like to work with it. Probably you are using it even if you don't know it, because some big companies like Google or Apple are using differential privacy when they train some models with your data. Google is using it when it's training the Gboard keyboard. And to start with differential privacy, I want to do an explanation, not using the models, the machine learning models, but with a simpler explanation using databases. That is the original purpose of differential privacy, as far as I know. First of all, I will do an example to give an intuition about how it works, and then I will try to give a more formal definition with some math. So suppose that you have two databases, and these two databases differ in one instance. For instance, you would have, in the first database, the black one, you have 100 patients. In the second one, you have 99 patients. And if you query both of them, you can have different results. For instance, you want to do a counting query, in the sense that you want to know how many patients have diabetes, for instance. And if you query these two databases, you may have as an output that in the first database you have 10 patients with diabetes, in the second you have 9. And this may be a risk for the one patient that is not in the second database, because you can infer something new about that patient that you didn't know before doing the query. If you want even simpler explanation of this, you can think about an attacker that, in the worst case scenario, knows 99 of the 100 patients. So you know everything about these 99 patients, and there is one patient that you don't know, and you want to know if this patient has diabetes. So if you do the query with this database, what happens is that you will have an output, and since you know the 99 of these patients, you will be able to understand if the last one has a certain disease or not. So what differential privacy does in this case is to add some randomization to this process, to the output of the query, basically. And you will have more or less the same output, regardless of the presence of a patient in the database. So instead of having exactly the same number, exactly the number of patients that has a disease, you will have this number plus some noise. So if you repeat this process multiple times, you will have multiple different results, because this process is random. And you will forgive me if I introduce some basic math here, because more formally, what I explain with this example can be summarized in this definition. If you have two databases, and these two databases differ in one instance, you can say that these two databases that we query, they will produce the same more or less the same output, and they will produce exactly the same output with similar probabilities. So regardless of, as I say, the presence of one instance. And the important parameter here is this exponential function here. And in particular, the crucial parameter is this epsilon that is called privacy budget. This exponential function tells us how much these two probabilities, how much the likelihood of having this output, how much they will be similar. And this is called privacy budget. And the idea is that the lower is this epsilon, the more is the privacy that you can guarantee. For instance, if you set epsilon equal to 0, you want to have exactly the same probabilities, regardless of the database that you are using. And this epsilon is one of the things that you should like about differential privacy, in the sense that it gives you an upper bound on the privacy loss. That is something that are other approaches that tries to protect your privacy doesn't have, basically. This is the classical epsilon differential privacy definition. There is a relaxed version of this definition, in which you introduce an additional privacy parameter called delta, and in this case, the delta quantifies the probability that something goes wrong. Basically, in this case, you will say that the mechanism will be epsilon differentially private with probability 1 minus delta. So you have to take care of this privacy parameter. So to sum up, the idea of differential privacy is that instead of returning the output that you want to return, for instance, for the query could be a number, you have to return this number plus some noise. And this noise is this has a cost, because based on the noise that you want to add, and based on the privacy that you want to guarantee, you can degrade a lot the result that you are releasing. So if you want epsilon to be equal to 0, you will have to add a lot of noise, and probably your query will be useless. So in this talk, I have to also discuss about neural networks, because this was just an introduction of differential privacy, and I think that it's useful because when we have to discuss about neural network and neural network trained with differential privacy, the idea is similar to the one that we have seen with the databases. I will do another example here. So if you think about two datasets again, and you train two different models, you will have two different models based on the dataset that you use. And if you think back to the previous slide in which I introduced the idea of membership inference attack, if you don't use any privacy protection during the training of these two models, you could be attacked by an attacker with using this membership inference. What differential privacy does in this case is to give you the guarantee that the likelihood of having the same output with these two different neural networks trained with these two different datasets will be similar. And the definition is, again, the same basically to the one that we have seen before. We have, again, our privacy budget with our exponential function, and the output of this neural network will be similar at the end when we release the output. There is a difference in the way this is implemented, because with the counting query example, what we were doing was just to add some noise to the output. In this case, differential privacy is not introduced when we release the output of the model. So it's not like with the example with the color of the cats. It's not that the color is 1, but we return 1 plus some noise. Differential privacy is introduced during the training of the model. And if we consider the classic stochastic gradient descent that is used to train neural networks, basically what happens is that we take a batch of data, and for each of these batches, we compute the output, and then we compute the loss, and we compute the gradients. Then we average these gradients. Differential privacy is introduced with an algorithm called differentially private stochastic gradient descent. That is, the shorter version is DPSGD. And it is introduced in these two parts. So basically what happens is that compared to the classic stochastic gradient descent, what happens is that we have to, first of all, we have to clip our gradients. So we have to choose a maximum value for these gradients. This clipping was not necessary in the previous example, because in that case we already knew that the difference when we were querying the two databases was at most 1. In this case, this gradient could have different magnitude and so we need to clip to bound the information of these gradients. And this is the first step that we have to add. So we clip the gradient, and then what we have to do is to, instead of just averaging the clipped gradient, we have to add some noise. This noise can be drawn from a Gaussian distribution, for instance, and the noise depends on our privacy parameter. So the noise depends on the epsilon, because based on the epsilon that we want to guarantee, we will have to find a noise parameter. And then it also depends on the clipping value that we decide to have. Because if we choose a small clipping value, we will have to add less noise to the clipped gradients. Because basically what happens with this noise is that this noise is drawn from a Gaussian distribution, and standard deviation of this distribution is the noise multiplied by this clipping value. And it is important to choose carefully these parameters, because if you choose, for instance, to use a high value for the clipping, you will have to introduce a lot of noise to guarantee differential privacy at the end. And at the same time, if you choose a low epsilon, you will have to introduce a lot of noise. So I don't know if I scare you with these things, but there is a good news, because luckily you don't have to manually implement all this stuff. There are implementation of DPSGD both for private PyTorch and TensorFlow. For TensorFlow, there is a library called TensorFlow Privacy. I've never used it, but for PyTorch instead there is a Opacus. That is a library maintained by Meta, by the PyTorch team, I think. And these two libraries are so especially PyTorch, especially Opacus, in my opinion, it's easy to use, and you just have to choose carefully your privacy parameter. Basically, what happens is that the good part about this library is that you don't have to make too many changes in your code. You just wrap your original model, your optimizer, inside this differentially private model. And this will take care of the training of the model using differential privacy. The important part here is that, as I said, you have to carefully choose your privacy parameter. You have to specify the epsilon here, you have to specify the delta, and the max grad norm, that is the clipping value. It's not easy to choose these values. In my experience, I usually treat the clipping value as an hyperparameter, so I search for the best one during the hyperparameter tuning phase. For the epsilon, there is no, I would say, a golden rule for picking the right epsilon. There are some papers that says that values between 1 and 10 for training a machine learning model are acceptable. Other papers says that even bigger values could be acceptable, because at least it's better than training without any privacy mitigation technique. This is something that depends on your model, on on the privacy risk that you want to consider. So, as I said before, with the example with the databases, the privacy parameters are important because you have to take care of a trade-off between the utility of the model and the privacy that you want to guarantee. If you decide to use an epsilon that is too small, again, you can use epsilon equal to 0. That is a small value for the epsilon. And to guarantee that the model is trained with epsilon equal to 0, basically you will end up in a random model because you want these two, the likelihood of these two probabilities to be equal. And so if you set a low epsilon, you will need to introduce a lot of noise. And this will degrade the model performances. So you have to take care of this. In my experience, again, I usually try multiple values of the epsilon, and then I try to use the one that is a good trade-off between the privacy protection and the utility of the model. So this is the end of the talk. Thank you for your attention. And
thank you very much. It was really interesting. Okay, so we have one question by now, which is why add noise during gradient descent and not directly to the input data, targets and features?
Okay, so in the case of this algorithm, they add noise. So they add noise during the training. I've seen that there are other approaches. It's not the only one. Some of the approaches that I haven't seen any. So maybe it's I haven't used any other approach, especially with noise on data. I think that it's possible. The other thing that I found is that in some cases, especially in some contexts like if you train the model using federated learning, I don't know if the person who asked the question knows it. In that case, I found that in some cases, instead of putting the noise during the training, on the gradients, they put some noise on the weights of the model before sharing them with the server. I haven't seen any example with noise on the data, but I guess that it's possible. There are also other, if you want to work with the data, there are probably other techniques that are, maybe there are not, I don't know too much these techniques because I mostly focus on this differential privacy, but I know that there are other techniques that tries to protect the data set and to try to give you some guarantee of the privacy. It's not as formal guarantee as with differential privacy, but they are more. I think it's older techniques than this stochastic differentially private stochastic gradient descent. I don't know if I answered the question or not. Okay.
Second question: if you give some examples on how you can add noise. How you can add noise.
So in the case of the PSGD, basically the noise depends on your privacy parameter, and it is managed by the Opacus library. You don't have to manually add noise, except if you want to do something different than just training the neural network. For instance, again, if you are in a distributed setting and you want to share some additional information, maybe you want to add noise, to manually add noise. But in the case of using Opacus, for instance, you don't have to manually add noise. It's managed by the library, and the only thing that you have to do is to choose the privacy parameter. So you just choose the epsilon, and then based on this value of the epsilon and based on the clipping, you will compute the noise. You can also, with Opacus, you can see every time that you add noise, you can see how much noise that you are adding, I think. I don't know if I answer. Okay.
I guess so. Okay, we have time, so I'll ask these two also. How do you test the effectiveness of the added noise?
I interpret the question like how can you audit then the addition of the noise is working, and so the guarantee that you have with differential privacy is a formal guarantee with this epsilon that tells you how much you will what's the upper bound for leaking some information. There are some techniques that tries to find a lower bound, in the sense that they try to use some of the attacks, like a membership inference attack, for instance, to find a lower bound on the attacks. This is a technique that maybe can be used to understand what's the lower bound in leaking this information. And since we have time, I will add also that there is a nice paper that maybe I will add in the references in the slides, and I uploaded the slides on my website. There is this nice paper that was published a few weeks ago, and they compare some alternative privacy mitigation techniques to the differential privacy, and they show that if you do a proper auditing using strong membership inference attack, differential privacy will always protect you more than other alternative solutions, or more than using basically any don't use any privacy mitigation technique.
Okay, last two, I think. Can you make some examples and common domains and application of differential privacy?
Yes, I don't know if I have it here. So I found two main applications that I wanted to tell you, but I removed the slide because I was not sure about the time. The first one is the one that I mentioned during the talk. Google is using differential privacy during the training of Gboard, and in this case they are using federated learning and differential privacy. So you are probably using differential privacy on your phone. The other another use of differential privacy that you are probably using without knowing it is on several services on Apple products like iOS or macOS. They use differential privacy in some part of the system. For instance, I know that they use it when you get a suggestion for an emoji. I think they are using differential privacy. There is a nice article. The number 8 here. It lists a lot of real-world use cases for differential privacy, and I think it's a nice article to see what are the use cases of differential privacy, and he also posted a lot of content about differential privacy, a lot of tutorials. It's a nice starting point to know more about this technique.
Okay, we have time for one last question. There are two. I like both of them. Okay. So I'll ask the first one. Okay, that came up. Okay, you discussed sampling from a Gaussian distribution to create the noise. Are there any benefits to sampling from distribution unknown to a potential attacker?
So it's not mandatory to use the Gaussian distribution. For instance, in the case of the counting query example, I think it's more common to use a Laplace distribution. Honestly, I don't know if there is a benefit in using the Gaussian one, but it's possible to use also other type of distribution. It depends also on the task. For another task, I try to understand a little bit how. So for the counting queries, I think I also found that it's possible to use other distribution like the geometric distribution. But yeah, I think that also in Opacus you can decide which one to use during the training. It's not mandatory to use that one.
Okay, so that very quickly, if the use of gradient clipping that is also used for vanishing gradients can interfere with the privacy. So if when you use gradient clipping for vanishing gradients, and can this interfere with the privacy?
No, I don't think that this can interfere. But maybe I didn't get maybe to the. Yeah. Yeah, we can also discuss later.
Like we use this parameter for two things at the same time, and that
Mm-hmm.
like I use it to enhance my model performance during training, but I also use it
For
this is privacy
I.
trick me out in some way.
So my guess is that maybe since I use it like I usually pick the clipping as a hyperparameter. Maybe it can be used for both. In both cases, it's an hyperparameter. So maybe it's just we can just pick one that it's the best one between all the possible values that you try. But we can also discuss about it. It's interesting. I have never thought about this. Thanks for the question. So thank you again.